Okay, so let's start the second class on astrobiology. So what we discussed in the last class is what was the realm of astrobiology, right? So what are we going to expect when we are trying to study astrobiology and whatnot? And we also saw how astrobiology needs different branches of science to like come in together and think about these very different processes. So it's not just one branch of science. It needs other branches of sciences to come in together to solve big problems. In this book, you will find life as one of the primary things that we'll discuss, like what are the different forms of life, or what different conditions in life can actually exist, and so on and so forth. But to start that discussion, we need to come up with a working definition of life, right? So like that's the first, that's where we can start thinking about like what is life. So there are many definitions of life. Okay, none of them are perfect. Okay, but we do not need a perfect definition of life to start studying life or astrobiology. What we need is a working definition. So something that kind of fits or checks most of the boxes and gives us a basic idea. But none of these definitions till now can check all the boxes. Okay, so you will see that this is a basic definition that NASA scientists have come up with. A self-sustained chemical system capable of undergoing Darwinian evolution. Okay, so all these words have been carefully put together. So self-sustained. Okay, so it has to be an entity that is able to exist on its own, right? So like a self-sustained chemical system capable of undergoing Darwinian evolution. Okay, in these forms of life, over time will be able to undergo evolution and Darwinian evolution, survival of the fittest, so Charles Darwin. Okay, based on this definition, let's start our discussions today. Okay, but before going into that is the modern definition. But even before, and I keep coming back to like definitions given by the Greeks and essentially the Greek philosophers, because you can see how deeply these people were thinking about 2,500 years ago. Even then, so like most of the philosophy of that time that you see, Socrates, Plato, Aristotle. So this, like, we generally, when we think about classical philosophy, we start with Socrates, Plato, Aristotle, but there were many people before that. So, who was this person who gave the a squared plus b squared equals c squared? Pythagoras, yeah. So he was a famous philosopher at that time. Mathematics was a part of philosophy. Biology was a part of philosophy. So Galen was one of the biggest philosophers. He was a philosopher of medicine, of medical sciences, things like that. So they were physicists at that time. So philosophy, you cannot just think about philosophy as in the modern definitions of philosophy. Philosophers like Democritus at that time were also thinking about the physical world. So philosophy was not just thinking about the modern philosophical things that we think about, what is ethics, justice and all that, but it was also about thinking about things in physical forms. So there were also metaphysics, but there was also physics as part of philosophy. So Democritus you can think of him as one of the atomicists who thought that the world or the universe is made up of atoms and absence of atoms, so like atoms and voids. So the concepts of atoms or atomos, which is like indivisible particles, which Dalton came up with, this is actually old idea. okay? Which is astounding. I mean, thinking about how people like these were thinking about the physical form, and they were very correct in thinking about these things. Also, there were others who were thinking about water or fire or air as one of the most important elements of life, which we kind of now know that they are not true, but there were also many who were pretty close to the modern understanding of the physical world. Okay. So one thing that Democritus and the atomicists they thought about is there is no difference between living organisms and non-living organisms as per what they're made up of. So they are all made up of voids and atoms. That was the major idea. But when Aristotle came in, and Aristotle is arguably one of the most famous philosophers of all times. So he has written so much on so many different topics, starting from the physical world to metaphysics. So he is considered one of the greatest philosophers. I have not read Aristotle that much, but personally, there are problems with Aristotle's theories at times. I think Socrates and Plato were much better philosophers than Aristotle, but Aristotle's views transcend to multiple disciplines, and that's one of the reasons why Aristotle is so famous. Okay. The other thing is Socrates never wrote anything. So Socrates was known for asking questions, and that's why we have the Socratic method of investigation, in which you ask questions to come to the truth. Okay, Plato was Socrates' student, and Plato wrote the dialogues, the famous Platonic dialogues, in which Socrates was one of the main interlocutors, as he used to say. Okay, so Socrates, and then came Plato. Plato was Socrates' student, and then came Aristotle, and Aristotle was Plato's student. So there is a very, very strong lineage. Okay, but Aristotle came up with this idea of hylomorphism, in which what he suggested is this. His idea was different from Democritus. While Democritus, in the previous slide, he thought that life, so living and non-living things, they were both made up of the same thing. What Aristotle said was something different. He said, no, you need a vital force of life that made living things living. That was his contribution. So he thought the hylomorphism has matter and then it has a form. And this form was actually the soul. Okay? This is a very strong idea. This kind of took all the living beings and made them something bigger and better than all the non-living things because of this form, because of that vital energy concept. Okay, now this vital energy also had different tiers of vital energy. For example, plants have vital energy, animals have vital energy, human beings have vital energy. But the vital energy in plants is less than that of animals, because in plants that vital energy is just helping them to grow, but it is not giving them any mobility or the type of mobility that the animals have. So the idea was animals' vital energy was better or greater than the vital energy of the plants. And for human beings, our vital energy is greater than the animals because we also have the reasoning power. So that was the logic of this hylomorphism concepts, right? So the rational soul is the highest form of vital energy that there is. This is it was a very popular and a very, it was very strongly established for about 2000 years. So this form of vital energy stayed there, and it said that a non-living thing plus vital energy becomes a living thing. That was the idea. So you take a non-living thing, add that vital energy, and that thing becomes living. That was the primary idea. But this was discarded in about in the 17th century. Okay. In that interim, there were many people who supported the idea of vital energy. They also wrote books or like texts like how to make mice. So they were like procedures on how to make living things. Okay. This was refuted after about like 1500, 2000 years, in which there was a simple experiment that was conducted. So the idea was, when you have meat exposed to air, you get living things growing on the meat. So meat was considered non-living. After a while, when the meat is exposed to the atmosphere, you start getting maggots or flies on the meat. And this is how non-living things become living. That was the idea. That was predicated for this vital energy, vital heat concept. But a small experiment changed or challenged or refuted this entire idea. What they did was they covered the meat, and they showed when you can keep this meat covered, you do not allow the flies to sit on the meat, you don't get any signs of life growing on that meat. Very simple idea of sterilization, but we are getting there. We are not there yet, because in here you have like a gauge with holes to not allow flies to get in, but then you can also have lid without the holes, and even then, like this is a much in this one you're not even allowing the air to come in. In here you're allowing the air, and sometimes there are microscopic forms of life that can come in through the air, and we have seen this in our labs, right? So like we have to actually cut, so there are microbes moving around in the air, and at that time there was no idea of like small microscopic organisms. So this was a very like I don't want to say earth-shattering, but it was a big challenge to the idea that no, life can only come from life. But still, this was a kind of challenged. But then came Louis Pasteur. This is the guy who came up with pasteurization of the famous Louis Pasteur. He came up with this very simple swan neck flask. So he made these flasks in which he showed that when you boil a mixture of, so you can think of this as organic soup, in which he had yeast extracts, pepper, water, and urine. So in which you boil this and you keep it open to the atmosphere, you can see microbial growth. Okay, but what he did, he had this swan neck kind of a flask in which the air is not able to come and reach here, or the microbes that are there in the air are not able to travel to this organic soup. In here, he firmly established that you can have no microbial growth in these kinds of situations. What other thing he established is this microbial growth or life is coming only from pre-existing life. So there was this Latin phrase that was used. I don't know it is here or not. That kind of meant that life can only come from life. Yeah, I don't have it here, but I've read it somewhere. So if life cannot come from abiotic organisms, can only come from life, that means anywhere you see a microbial things growing or maggots growing, that means there was some form of pre-existing life that produced that kind of life form. But what is the problem with this approach? This is true that a biotic life can only come from life. Like say, you cannot have abiotic things producing life. So biotic things from biotic things. Like you need a precursor, an organic or life precursor to breed. So life breeds life. Non-life cannot produce life. Like that's the basic idea. But what's the problem with this idea?
How is the fast that precursor is formed?
Origin of life becomes a problem in here. So that's what a major problem of astrobiology currently is. So we are also trying to find out how was the first life produced. This cannot solve that problem. Okay. So with this, the idea of life needs to be discussed, right? So like what is that life, right? So we came up with this idea of self-sustaining chemical system. Okay, life can also exhibit complex behavior. Okay, whatever that complex means. So like even when you see a microorganism, a single-celled organism, that is also very complex, very complicated. So life is not simple. Life has, so the simplest forms of life are also too complicated. Okay, so that is one of the characteristics. Okay, complex. You can also have, so the self-sustaining chemical system is the thing, like if you have a cell, it has a cell wall that kind of differentiates itself from the outside world. So the inside versus the outside, and there are interactions through that cell wall from the outside world. Okay, that's another thing. It also metabolizes. What is metabolism? Very simplistically,
breaking down complex.
So you're eating.
Yeah.
So you need energy for survival, like that is. So you metabolize things, right? So that's what you're trying to do. Then the problem that comes in here, so there are many different forms of characteristics that people have come up with. In the book you have things like MRS-GREN, so movement, respiration, sensitivity, growth, reproduction, excretion, and nutrition. So these are the different characteristics of life as we think about. But there are two problems with this. There will be certain non-living things that will, or non-living by our general idea. Okay. There will be certain non-living things that will do some of these things. So how do you differentiate that? And there will be certain living organisms that won't do all of these things. So it becomes a little bit complicated. The waters get muddied. Okay. Now let's see some of these things. For example, storms, which is coming. So like a hurricane is not coming in, but we are expecting bad weather during the weekend. So weather patterns, something like that, have many such characteristics that living things have. So they are sensitive to changes in the environment, they grow, they can move, and all that. So, but we don't think this is living, right? So it's a complicated system. Sometimes it is a chemical system, but most of the time it is physical. But rain, storms, these are also chemical systems, but they are not living, right? Fire, it does, you can also think that it is doing those metabolizing processes that we tend to do. So we take organics, we burn them, and that's how we get the energy. Fire does that. It can grow, right? It can interact with the environment, but this is not a living thing. Minerals, they can grow, but certainly these are not living organisms. There are certain organisms that seems like they are living, like viruses, but they are not living beings as per the traditional, acceptance of like the living. So viruses are not living. So they can stay dormant until they hatch onto a host and then become living. Okay, so what would you think of viruses as living, non-living, somewhere in the middle? So it's kind of complicated. The other is there are certain organisms, like certain organisms on Earth that do not reproduce. Okay, but we certainly don't think of a mule as non-living. It is certainly living. So none of these definitions are perfect. Like that's what we have to keep in mind. The idea is, again, why do we need that stringent definition? Because when you look into a different planet for life, what would actually tell you that there is life or there was extinct life? So Joel's paper, like the 2025 Nature paper, Horowitz, that is also that, right? So we don't typically have, we are not seeing some organisms moving on the surface. We have some chemical signature, and based on that chemical signature, we are trying to backtrack and trying to understand, was there life? Can there be life? And that's why we need a good definition of life, because then we can come to a consensus of biosignatures, like what could be potential biosignatures. So fossils could be biosignatures, right? So if you have a footprint of a dinosaur, that is a biosignature. You could have chemical biosignatures, like there could be certain chemical compounds that can only form through life. So those could be biosignatures. There could be isotopic signatures, okay, and we'll look into that. So that's why we kind of need a definition. But the other definition of life was self-sustaining chemical systems that is capable of Darwinian evolution. But the problem, what is the problem with this definition when it comes to detecting life on a different planet? Can you see Darwinian evolution when you are looking at a one point? You don't. You are seeing a snapshot. And Darwinian evolution is you need to look into something for a period of time. So that's another problem. So if something is living, quote unquote, how do you know it has undergone Darwinian evolution? We don't. So there's a lot of problems even with the definition. Not problems, but there's nuances to actually thinking about life in general. Okay, I did not do that. The other definition came from Schrödinger. Like this is the famous Schrödinger's equation, Schrödinger. At one point of time, he has also written a book, What is Life? Okay, and there are many scientists today, and I shared 2 videos on our Canvas page that deals with what is life. So there was by a Nobel laureate. Okay, so what is life? These definitions are very central. These are not philosophical. They have a real meaning in scientific terms. Schrödinger wanted to deal with life from the idea of thermodynamics. Okay. So let's look into this thermodynamics definition a little bit. So it is not perfect, but let's see if I can. I don't want to delete it completely. I will just leave it at that. So is this visible? Yeah. So we know right? So this is the Gibbs free energy. Okay, very simplistically, I'm not going into the details. What is delta H? Enthalpy, exothermic, endothermic, all those reactions. What is delta S? Or delta H is change in enthalpy. Delta or S, what is S? Entropy, right? Entropy is also generally talked about as a disorder. There is a law of thermodynamics that says that the entropy of the universe is always increasing. Okay? That means the universe is going from order to disorder. This is the natural flow of things. So as I also talked about in our geochemistry class, if you don't spend any energy on making things or arranging things and keeping them in an orderly manner, what will happen? Things will become disorganized with time. You don't have to spend any extra energy to make it disorganized. That's the nature of nature. Things become disorganized. You don't have to do anything to make something disorganized. It will anyway become disorganized. You need to spend energy to reverse this process. So like if you want to make something orderly, you have to spend energy in doing that. Imagine life as a chemical reaction. Also, the Gibbs free energy is when is a chemical reaction feasible? When the delta G is negative or positive? It's negative, right? So when delta G is negative, then it becomes feasible. So let's see, if life is a chemical reaction, how do we actually think about the entropy and the delta H? So what do you think our life needs in terms of entropy? Are we ordered chemical entities or disordered chemical entities? Do we need specific chemicals in specific order at a specific time, or we are fine with any order, whatever? What do you think we need? Do we need order for sustenance or disorder? We need order for sustenance. We need specific things in a specific order for us to sustain life. So the delta S, so we need order. Okay? So the delta S of life. Tell me, what is the delta S of life? Is the delta S positive or negative? Think about it for a moment and then tell me, what is the delta S of life? Think about it. Take a minute, think about it.
If delta S is positive, means it is going to disorderliness, or like increasing entropy means disorderliness?
Yes.
So,
Yes.
so if life is an ordered system, then delta S should be negative?
It's negative. Okay, let me write that down and then we'll discuss it. Delta S of life should be negative. Why? Because we need order. And S is entropy or disorder. So what we need is the opposite of entropy. Okay, that is why we need a negative entropy. So we need from disorder to order. So when we are going from disorder to order, do you think the entropy increased or decreased? When you went from disorder to order, decreased, right?